The turbocharger, or turbo as it's generally called, seems to have acquired a certain mystique, but in fact its principle of operation is a simple one. In practice, providing it's used and maintained properly, it's a perfectly reliable device. In the event of a malfunction, however, the diagnosis and repair of turbocharger faults is relatively straightforward, provided that the operating systems are clearly understood and your approach is methodical. In this training video program, we're going to look at the principles of turbocharging, the operation of the individual components, and the 3 different control systems currently in use. Remember to stop the tape when requested. So let's look at the reasons for turbocharging an engine. The main objective is to greatly increase the performance of an engine without increasing its size. The benefits are that the desired increase in performance is achieved without increasing the weight of the engine. The manufacturer can use an existing and well-proven unit to extend the engine option range, and by using the smaller engine, the bonnet line can be kept lower, improving the aerodynamics, and hence the vehicle's performance and fuel economy. The principle of turbocharging is to use the high-speed waste exhaust gases to drive a turbine, which, through a common shaft, drives an impeller. The impeller forces air into the inlet manifold, where it mixes with the fuel. The mixture then passes via the inlet valves into the combustion chambers. Because the mixture has been compressed, a greater volume of air and fuel enters the cylinders, which increases the efficiency of each firing stroke, thereby increasing the power output of the engine. It must be borne in mind, though, that this increased efficiency can only be achieved when the engine is developing sufficient exhaust gases to drive the turbocharger quickly enough to compress the intake air. This is calculated by each manufacturer to suit the individual requirements and vehicle applications. The applications we're going to look at are for the 1980 to 1983 Audi 205T, the Audi Quattro, the 1984 Audi 205T, and the Audi 80 Turbo Diesel. They all have similar basic components, but the control systems differ. The main parts of the system are the turbocharger itself, the wastegate, which limits the maximum boost pressure, the overboost safety switch, which, should the wastegate malfunction, switches off the fuel supply or limits the engine RPM, depending on the model. The ignition advance and retard system, which is controlled either by 2 delay valves or, on the later vehicles, by the electronic ignition control unit, the intercooler, which is used to improve the efficiency of the turbocharger by cooling the charged air, and on turbo diesel engines, a dump valve is used in place of the overboost safety switch to control overboosting should the wastegate fail to open. Another difference is that the wastegate is an integral part of the turbocharger on turbo diesel engines. Let us now take a closer look at each of the components. The turbocharger can be broken down into 3 areas. 1, the turbine wheel and housing. 2, the lubrication and bearing housing. 3, the impeller and compressor housing. All 3 are bolted together as one unit, and there are no repairs or adjustments. In detail, the turbo works like this. The engine exhaust gases are directed onto the turbine blades via the channels in the turbine housing, driving the turbine at high speed. The impeller is driven at the same speed through the common shaft. At idle and lower part throttle openings, the exhaust gas flow is not fast enough for the impeller to compress the intake air, and so the engine operates as a naturally aspirated engine. As the engine speed increases, so does the exhaust gas flow, and so the impeller is driven more quickly. At medium part throttle, approximately 3000 RPM, turbocharging begins to take place when the inlet air is compressed and supplied to the cylinders at atmospheric pressure. At upper and full throttle openings, or engine speeds above 3000 RPM, turbo boost builds up quickly and would continue to build up to pressure which could damage the engine. This is prevented by two controlling influences, the first of which is the wastegate, which we'll look at in the next section. Stop the tape and refer to the workbook. The wastegate controls maximum boost pressure. It does this by opening to reduce the exhaust gas flow through the turbine by wasting it directly into the exhaust system. This slows the turbocharger down, limiting the maximum output from the impeller to between 0.8 and 0.9 bar. There are two different methods of operating the wastegate, one by boost pressure and one by exhaust gas pressure and depression. We'll look at the exhaust gas one first. It operates like this. At idle, lower and medium part throttle openings, the spring keeps the valve closed. Between the spring and the valve is an operating piston and diaphragm. Exhaust pressure is applied to the valve side of the diaphragm and depression to the spring side. Once the engine speed is above 3,000 RPM, that is, the upper to full throttle range, the boost pressure builds up rapidly to 0.8 bar. The exhaust pressure acts directly against the head of the valve and, via a pipe, onto the valve side of the diaphragm, partially opening the valve. This reduces the boost pressure to approximately 0.6 bar. As the engine speed increases further, the gas flow and pressure also increase, and the valve continues to open. To ensure that the valve opens still further at an appropriate speed to prevent the engine from pinking, the diaphragm movement is assisted by depression, which is channeled via a flexible hose from in front of the impeller, where the depression is created by the increased speed of the intake air. The combination of exhaust pressure and depression ensures that the boost pressure is maintained at the optimum figure of approximately 0.6 bar. The function of the boost pressure operated version of the wastegate is exactly the same, but the operational characteristics differ in the following way. Firstly, the spring chamber is now open to atmospheric pressure via a short piece of hose. Secondly, the only operational chamber is the one on the valve side of the diaphragm, which is now operated by boost pressure. It works like this. Once the engine speed reaches 3,000 RPM, the exhaust pressure acting on the head of the valve and the boost pressure acting on the diaphragm open the wastegate and relieve the initial build-up of inlet manifold boost pressure. As the engine speed increases, the greater volume of exhaust gas flow and the now stabilized boost pressure fully open the wastegate, maintaining the inlet manifold boost pressure within the desired values. The use of boost pressure to operate the wastegate instead of exhaust gas pressure has the advantage that it cannot carbon up and reduce the efficiency of the wastegate. If the wastegate should fail to open, the boost pressure would continue to increase to a point where engine damage would occur. This is prevented by the Overboost safety switch, which will limit excessive boost pressure to approximately 1.2 bar. There are two methods of doing this. The early version is a mechanical switch, and the later version is electronically controlled. The mechanical boost pressure operated switch is situated in a bypass hose attached to the inlet manifold at the rear of the engine. When the boost pressure is below 1.2 bar, the switch contacts are closed, which provides the earth for the fuel pump relay. When the boost pressure exceeds 1.2 bar, the switch contacts are opened and the earth for the fuel pump relay is interrupted. As a result, the fuel pump is switched off, engine output is interrupted, boost pressure drops, and so the switch closes again and normal operation is resumed. The electronic version limits the engine's maximum speed to 4,000 RPM by causing a misfire. The operation of the electronic unit is explained in the training video program Ignition Systems. On turbo diesel engines, this task is performed by a dump valve, which is designed to open at a predetermined pressure. Stop the tape and refer to the workbook. As the turbo is exhaust-driven, heat from the gases is transferred to the turbine wheel, housing, shaft and bearings. Compression of the air also generates heat, and so lubrication and cooling are very important considerations. Cooling is carried out by heat dissipation by oil from the engine lubrication system. The oil flows under pressure through the upper drilling into the bearing housing and onto the bearings. The turbine side of the bearing housing is cooled by an oil pressure drilling, and the oil returns directly to the engine sump via the lower drilling. It's very important that only the correct grade of SF oil is used in turbocharged petrol engines. With diesel engines, an SHPD specification oil must be used. It's vitally important to the reliable running of turbochargers that only these oils are used on the correct engine. The SF and SHPD specifications have the correct characteristics to be compatible with the respective fuels. They can stand the higher operating temperatures and are more resistant to carbonizing. It's the carbonizing of the oil in the bearing housing which can restrict the oil flow, impairing the lubrication and cooling processes which can lead to premature failure of the turbo. The owner should be informed at the time of purchase that the engine should be allowed to idle for at least 1 minute before switching off. This allows sufficient heat to be dissipated from the turbocharger by the oil circulation, preventing carbonizing of the bearing housing. A further improvement for 1985 will be the introduction of a liquid-cooled turbocharger. Stop the tape and refer to the workbook. The increased efficiency of the turbocharged engine necessitates more accurate control of the ignition advance and retard curve. There are two methods of achieving this. The early Audi 205T used a mechanical system. The Audi Quattro and the later Audi 205T use electronic control. So let's have a look at the mechanical version. This is achieved by the use of one-way delay valves. These valves are basically one-way valves, but they do have a small ventilation drilling that allows movement of air at a controlled rate in either direction. This enables pressure to equalize smoothly. To identify them, they are the largest black and white valves located in the retard pipe at the rear of the engine. They should be back-to-back, that is, black to black. The advance pipe is connected to the throttle housing at a point just above the first stage throttle valve. The retard pipe splits into two at a T-piece, firstly via valve number 1 to in front of the turbo impeller, and secondly via valve number 2 directly into the inlet manifold. There are several phases of operation which we'll take one at a time. During idling, there is a depression in the inlet manifold which is channeled through the hoses via valve number 2 to the retard side of the distributor's diaphragm unit. The atmospheric pressure from the point above the first stage throttle acts on the advance side of the diaphragm and pushes it into the retarded condition. The ignition timing is held in the retard direction when idling. When the throttle is partially open and the engine speed is below 3,000 RPM, a strong depression is created between the open throttle and the advance drilling. This depression is felt on the advance side of the diaphragm. A weaker depression or higher pressure is felt via valve number 2 on the retard side of the diaphragm, moving it into the advance condition. The ignition timing is advanced during acceleration up to 3,000 RPM. When the engine speed reaches 3,000 RPM, The turbocharger boosts the inlet manifold to atmospheric pressure. Therefore, both advance and retard pipes have atmospheric pressure in them, which acts equally on both sides of the diaphragm. Equalization of pressure takes place through the delay drilling in number 2 valve. Only centrifugal advance is maintained at 3000 RPM. At engine speeds over 3000 RPM, the turbocharger is boosting the inlet manifold above atmospheric pressure. The boost pressure travels down both the advance and retard pipes, but is prevented from reaching the retard side of the diaphragm by delay valve number 2. As a result, the boost pressure acting on the advance side of the diaphragm pushes it in the retard direction. Movement of displaced air takes place via valve number 1. In the upper part throttle range, the ignition timing is held partially retarded against centrifugal control. As the engine speed increases still further to full throttle, the boost pressure will have reached its control limit and will be pushing the diaphragm further retarded. This is assisted on the other side of the diaphragm by the depression created in front of the impeller via valve number 1. The ignition timing is moved to the fully retarded condition against centrifugal control. The electronic version of ignition control is fully explained in the videotape Ignition Systems. Stop the tape and refer to the workbook. The Audi Quattro and 1984 Audi 205T both have an increased power output made possible by the use of an intercooler. The intercooler's function is to reduce the temperature of air being supplied to the cylinders. It's placed between the turbocharger and the inlet manifold and is situated in the airflow behind the front grille. The operation of the intercooler relies on airflow through the matrix. The faster the vehicle's road speed, the faster the airspeed through the matrix, and so the greater the cooling efficiency. When the vehicle is being driven at engine speeds above 3000 RPM, the turbocharger is pressurizing the intake air, which heats it up considerably. So the air is passed through the intercooler, which, when at its most efficient, cools the air entering the cylinders by 50 degrees centigrade. The greater expansion rate of the cooled air, along with its increased volume, results in greater efficiency of combustion and so higher power output. These higher compression pressures necessitate a stronger and more efficient spark. This is best provided by an electronic ignition system. Stop the tape and refer to the workbook. Turbocharger faults fall into two main categories: the vehicle which is not going as well as it should, and the vehicle which is going too well. Few owners, of course, complain when the vehicle is going better than it has ever done due to overboosting, unless, of course, the engine is making knocking noises or it keeps cutting out. However, let's take the overboosting situation first, as this is usually the easier of the two to establish. The first step is to road test the vehicle. Select second or third gear, accelerate at full throttle, and see what the boost pressure gauge indicates. For vehicles without a boost pressure gauge in the dashboard, you will need to use VAG 1397 boost pressure tester. The gauge should go rapidly to 0.9 bar and then drop back to approximately 0.6 bar when the wastegate is fully open. If the gauge goes above 0.9 bar and stays there, then the vehicle is overboosting. If the pressure reaches 1.2 bar, the overboost safety switch will operate and the vehicle will appear to misfire. When road testing turbocharged vehicles, it may be necessary to reach high speeds in order to make the relevant assessments. Remember that 70 miles per hour is the speed limit on dual carriageways and 60 miles per hour on single carriageways. Make road safety your main concern. Choose your location for such tests carefully. Always be attentive to road conditions and circumstances, and do not maintain high speed any longer than is absolutely necessary. In the event of a mishap or prosecution, it's your license. Overboosting will occur if the wastegate is only partially opening, or not opening at all. The most likely reason for this will be one or more of the following. The exhaust pressure pipe to the wastegate is blocked completely, partially restricted, or broken. The vacuum pipe to the wastegate is not connected, kinked, or split. The wastegate diaphragm is damaged, valve stem is damaged limiting movement, valve stem is seized, or valve return spring has been tampered with and adjusted to too strong a setting. The later boost pressure operated wastegate can only be affected by the last 4 items or a kinked pressure pipe. Once you've located and rectified the fault, repeat the road test procedure. We mentioned the overboost safety switch operating and the vehicle misfiring. Should this happen on the original Audi 205T, when the boost pressure is approximately 0.6 bar, then the following areas should be checked. The earth for the boost pressure switch by using the current flow diagram, the brake pedal switch, the overboost pressure switch. These areas can be confirmed firstly by temporarily grounding the live feed wire of the overboost safety switch to earth and road testing the vehicle. The engine should not cut out when the boost pressure exceeds 0.6 bar. On the later Audi 205T and the Audi Quattro, the overboost safety switch is built into the electronic ignition control unit. Diagnosing and checking this system is dealt with in the video Ignition Systems. So much for overboosting. If the problem is underboosting, then there are other aspects to take into account. But once again, start by road testing the vehicle and confirm by use of the gauge in the dashboard or VAG 3097 that the vehicle is in fact underboosting. If a low boost pressure is confirmed, let's say 0.4 bar, the first consideration should be the condition of the engine, because an engine down on power will not produce sufficient exhaust gas pressure to drive the turbo fast enough. Therefore, all basic engine settings and adjustments should be checked and rectified before condemning any part of the turbo system. Having rectified any engine faults and repeated the boost pressure test with VAG 3097, if the pressure is still low, the wastegate should be removed and the valve checked for sticking open, burnt seat, a burnt valve, or a broken spring. If any of these faults are apparent, the unit should be replaced, since there are no repairs to the wastegate. Carry out another boost pressure test. The pressure should now be correct. In the event that the boost pressure is still low, the turbocharger should be removed and the shaft checked for freedom of rotational movement. The end float and side movement of the bearings should be measured using a dial gauge. There are no repairs to the turbocharger, and so if the shaft is stiff, bent, or the measurements are outside the tolerances, it must be replaced. This video should help you build up your confidence to diagnose and repair vehicles with turbochargers. However, only working with the vehicles will increase your experience and allow you to fully develop your skills.